Okay, let's begin. First of all, I would like to introduce myself a little bit. My name is George Zhou. I graduated about 15 years ago from UBC. Also, I got PhD degree from Tongji University in geotechnical engineer. And today our topic is about how to prevent foundation failure in a new residential construction. We have about 5 parts for today's topic. Probably we don't have time to finish all of them, but I will try my best. Hopefully we can finish first 4 parts. So the part 1 is about statistic analysis for foundation failure in Canada. And part 2, I will talk about lower mainland geotechnical conditions. And part 3 is how to deal with soft ground. Part 4 is how to deal with slope failure in sloping ground. Part 5 talk about remove bedrock. I think somebody might be very interesting, but I don't have slides here today. Anyway, we might have no time, but if we have time, we can have a short discuss about it. Okay, the first part, this is a static analysis of foundation failure in Canada. Those static analysis was done about 10 years ago, and the reason I use the date for 10 years ago is just it's fairly difficult to get this date, especially recent date. Any failure, people don't like to talk about it so much. So those data are insurance company, they send out the inquiry to all those owners who suffer from the failures, and this is only one of the data available I have. So the absolute number for the dollar value probably is not accurate because it was 10 years ago. But the interesting thing is the percentage about failures, the failure distribution among all those countries, among all those provinces. I will show you later on. Okay, this one is the failure in new residential. You see that's on the 1994 and 1995. In the British Columbia, the dollar value, you don't need to look. Well, you can look at dollar value, but you see the number, we have 43 failures in the 94, and totally overall in Canada we have 164. So in BC we have about 1/3 failures happen in BC. The same thing, actually in the 1995 about half of them happen. Totally overall in Canada we have 88 failure cases, but in British Columbia, in BC, we have 42. So that's implies we have lots of failures here locally in BC. And this slide you see that gives us a percentage failure, the failure ratio per 1,000 new building. So in BC, every 1,000 new building we have about 2 case failure. This ratio is quite high, but actually compared to other provinces, the other province is much higher, especially in Newfoundland. And the reason they have high failure because of 2 reasons. One is they don't have enough engineers, especially good engineers over there. And the other reason is about the weather. The weather over there is fairly cold, so they have lots of permafrost problem. This one is very interesting thing. The failures divide into different reasons. You see, most reasons is because of adhesion of ground, which means related with permafrost. And luckily here locally we don't have these issues. Especially in lower mainland, the frost depth is fairly shallow. But if you take the half of them away, you see all of those things can happen in BC. Most of them, like the clay, means soft ground. If we take this out, the soft ground is one of the major reasons, right? This is the highest one, this second highest one. But in BC, we don't have this problem. So the one of the major reasons is about clay, means soft ground. And the second thing is field settlement, also related with the compaction of field material. The next biggest one is slope failure. So later on, we will talk about all of them, like the settlement, like the soft ground, and slope stability. So that's why today we have the topic, like I mentioned previously. Okay, the conclusion from the part 1 is most serious foundation failure is for the soft ground, for the soft soil, and occurring in British Columbia, also all over the western part of the province. So my recommendation to everybody here is site analysis is fairly important. So every site we need to do geotechnical site investigation and understand the soil condition first, and then we can do the design properly. Now, next one I will talk about part 2. Maybe somebody, if you come previously, you are fairly familiar with this already. Sorry, I got to. Hello。哎，不好意思，我正在讲课。你那个，我带钥匙，我进来了。那个，我那个叫什么支票你拿的了，是吧？我没看见。在讲课的那个桌上啊。讲课桌上，那行，我知道，好 ，OK， 哦，那行，谢谢 ，OK， 拜拜，拜。Sorry about that. Okay, and because we talked about this already, maybe one of you might still be very interesting, but maybe I can go fairly quickly. It won't take long time. We will use more time for this third part and fourth part. This one actually is a superficial geological map in Lower Mainland, all the way from Vancouver, west end of Vancouver, all the way to the Abbotsford. And in this map, the condition, the information they give is not only superficial geological condition, but also about landsliding, about liquefaction, about floodplain. And in this map, I think if I have linked, it's not very clear, but if I can go, I need to copy this one. So this is internet, right? So if we come to here, that is the website, which is public, which is government public information. Everybody can access. So it's free information for everybody. So in this map, you can see different sites, like different area. For example, in Richmond, we have two different. Most of them, west of number 3 road is one color, and east of number 4 is other colors. So the color, this color they say number 2, or number 3 maybe. I don't know how to enlarge. Okay, we can enlarge it. and this is number 2, this is number 3. If you read here, the legend tell you number 2 is the P, means organic material, and this area organic material is fairly soft and fairly high water content. If you put foundation directly on this soil, the water will be squeezed out and the foundation will settle a lot. So most of the time, if we build anything here, we need to do preload or we need to use pipe foundation. And the other side, which is silt and clay, also fairly soft in Richmond area. They have fairly high water content, and this material, they have fairly low plasticity index, means during earthquake it can liquefy. So for this area, we need, when we design the foundation, you need to have a crush layer so that during earthquake, after the underlayering material liquefied, you have a temporary enlarged footing can fail the punch failure, can prevent punch failure. So this richness, if you look at the other side of Fraser River, which is Vancouver, Burnaby and Coquitlam, so the color is green, and this is type 7 material. Type 7 material is teal. Teal means the material was crushed by glaciers during the glacial ages, and those material is a kind of material between rock and soil, so they have very high capacity. And if you look further north, then you have purple color, which is bedrock. So the bedrock is fairly good, but bedrock, they have their own problem. Like in the North Vancouver, in the West Vancouver, the city required any development for one unit. You can only remove the bedrock within certain amount. Like I know in West Vancouver, they allow a single house remove only 600 cubic meter material. So if you remove more than that, you have to revise your design. And if we look other way around the upstream of Fraser River, like in the Surrey area, we have clay, which is type 6. We have clay and silt. This clay and silt is quite different from the clay and silt in Richmond West End, because it's deposited at higher level. The water content is lower, and relatively speaking, the capacity is still low, but slightly higher than in Richmond. So anyway, this is the public data. Everybody should pay attention when you purchase land. You should read this map first and got to understand what material, what soil you are dealing with. Okay. Let's go back to our PPT. Having talked about this, actually the soil condition is much complicated than we are talking about previously. For example, in Vancouver, we say the condition is fairly good, but actually it's not exactly true. Locally we have some variations. Like this map show you, we have 18 spots, very famous spots. This area is the location you have a P. So overall, Vancouver is good, but you still need to pay attention to this particular location. The other thing you need to pay attention when you purchase land is the historical use of the land. Like this is also available online. In addition to the 18 spots, which is P we talked previously, in this map, they also show you, the green line. Those green lines are the stream, which previously, like 100 years ago, or even earlier, they have creek, and this creek was filled. So if you build a house in this area, you need to pay attention. Like a few weeks ago, I have a site in the English Bay near Alberta Street. So this area, they have existing building over there. When we go over there to do site investigation, we hit the peat ground, which was in before 1982, a time when the old house, extinct house was built, the creek was filled, and they have not removed the soft ground. So right now, we will demolish the house and build a new one. So we found, well, this is a problem. We need to think of how to deal with it. Okay, so if you have very weak material like peat, like soft clay, and city bylaw, they have requirement for the foundation design. Last city require geotechnical report, but right now they didn't make it mandatory that geotechnical engineer design foundation. The structure drawing can show the foundation design, but they ask the structure engineer need to refer to the geotechnical report. That's the current requirement. So the summary for part 2 is, overall, the lower mainland, the site soil condition varies significantly, and we have very soft land to very hard ground. And soil type can be very different a few steps away, and some area they are fairly steep, like in the north part, in the North Vancouver, the ground can be over 25 degrees, so they have slope stability issues too. And also lots of area they have a liquefaction hazard in the earthquake condition. But anyway, those data is publicly available data. Is free. Everybody can access to it. And also, my company can provide all those data to you. In addition to the public data, we accumulate lots of boreholes in lower mainland areas over the last 20 years. So it's really a good idea. By the time when you make decision to purchase the land, you need to ask your realtor. If realtor have no geotechnical background, you better to ask a geotechnical engineer. That's part 2. Well, we go very fast. I think we still have time. Okay, now I would like to talk about part 3, which is while you do every effort and you found, you talk to your realtor, you talk to your technical engineer, and the ground is not good, and when you purchase land, you in the contract you say you make a term say subject to remove to geotechnical report. And by this time you got this land, and you hire a geotechnical guy come to the land to do site investigation and found the area do have soft ground, and then at this time we need to deal with soft ground. Soft ground is not at the end of world. We geotechnical engineer, we can deal with it anyway. We have different way to deal with it. Some of them is fairly cost effective. For example, if the soft ground is not so deep, like less than 2 meters, shallower than 2 meters, and the water level is over 2 meters deep, for this condition, usually we can use replace soft ground, and means you do excavation and remove the soft soil and replace it with sand and gravel and compact it layer by layer. And after you doing so, you can put your foundation on the compact material. That's method 1. And option 2 is if the soft ground is very, very thick, over 2 meters thick, by removing the material, actually is not economic and not feasible sometimes, because the neighboring close by can be damaged if you dig too deep. So at this scenario, usually we have to use preload. What means preload? Preload means we pile sandy material and leave the sandy material at the site for a few months to 1 year or even longer. And the third option is pile foundation. For preload, when we do preload, the ground will settle, and it's only applicable for the condition when the land is fairly wide and you do have lots of settleback from the utilities from existing buildings. If the existing utility or existing building is fairly close by, then preload may damage the neighboring existing structures. In this scenario, then you have to use pile foundation. So pile foundation, here in Lower Mainland, all kinds of pile foundation was used, such as timber foundation, concrete, steel, and we also have helical pile condition. And helical pile condition actually right now become very popular because helical pile can be installed without vibration, without contamination, without noisy, and soon after installation, you can put your structure immediately on top of it. They don't like the concrete pile. While you put the concrete, you have to wait 1 day, 2 days while they gain the strength. Then you can put the loading on it. So that's the good size. That's why it become popular. And for the residential building, quite often most people also use tin pile foundation because it's cheap and easy to use and easy to be installed. But pile foundation, the thing is, while you drive it, especially in the soft ground, they do have some vibrations, and you need to make sure while you install it, you need to monitor the vibration on the ground. The other thing for the tin piles is for the decaying, the sections permanently underneath the wall table, it will not decay, it will be good forever. And the portion always above the ground is also okay. But one section is sometimes it got submerged, sometimes it become dry. For this section, because the wall table fluctuate seasonally, those sections can decay. So you need to pay attention. Usually, previously we need to put some chemical material so that I don't know what chemical the name is, but anyway, that's one of the reasons the tin pile right now is not so popular. Okay, actually this one, like for the further description of replacement, actually we mentioned that already, right? I think we told this already. This one of the example, the site condition, we use the replacement, which is in number 6 load. And in a farmland, we did site investigation, and this is the soil condition. The top, like 1.2 meters, you can see from 0 to 1.2 meters is organic peat. Organic peat. The top is filled, and of this, we still have some silt. But if we have 1.2 meter of material for the residential building, is good enough. So for this case, we decide to remove the top 1.2 meters material and then build it that way. Here is the way, the building go over there. The top 1.2 meters material is removed. But be careful, when you remove, you got to remove slightly larger. The footprint is slightly larger than your building. And you got a slope like 2-to-1 slope. And while you do excavation, you do excavation this way. So excavation area is also larger than the area you put back the material. And the other thing I want to point out is this building is sitting in a flat plate. So the basement level can only use as crawl space and garage. The total height, actually the full height, but after we build it, we backfill it with EPS material. So this is the EPS put on top of it, so that we don't have settlement issue. Because if you still remember the borehole log, after 1.2 meter materials, we still have soft clay. So the soft clay can also settle. So we did some calculation and make decision with this area where you backfill this 0.6 meters. 0.6 meters should be lightweight material. Okay, and the second option, we talk about preload already. For preload, I think for every builder, you need to be careful. Preload not as simple as just dump some sandy material aside and leave it for a few months, then remove, you can build it. No, the things is not so simple. Actually, the right way to do is we need to do site investigation, and we need to do the preloaded design. To determine the preload height, how much material, how high and how big the footprint we need to preload it. Especially for some area, if you develop in phase, like phase 1, phase 2, usually, for big area, if you are using the preload, usually the land is fairly large area, and most builders would like to build it in phase, so that you don't have problem of cash flow. And while you're doing this, you need to make decision how big the phase 1 need to preload, and make sure the next phase preload will not impact the phase 1 structure. So those things you need to take into account. And the other thing is preloaded design need to consider how long the preload need to be sit on the ground, because preload is cheap, but actually the risk is the longer you wait, the marketing condition will also change. So you don't like to wait for too long. No. But for preload anyway, you need some time anyway. But if you don't like the risk at all, maybe for any area that you can use preload, you can still use pile foundation. The pile foundation is relatively expensive, but you can build immediately. You don't need to wait. The preload design, actually, for the time and height, when we design it, we need to take some soil samples aside and do a 1D consolidation test in the laboratory and find compression index and compression coefficient. And you need to know the drainage layer distribution. And based on the 1D consolidation theory, you can predict how high the preload will be and how many months, how long the preload need to be at site. In addition to this, after you dump the material on the ground, you also need to do the settlement observation. And this slide shows you the observation means settlement first time. Here is settlement, here's time. So after you dump the material, you have 4 or 5 spots which you have rebar extend from the base all the way to the top of the sand, and the survey guy need to come. The first week they come probably every day. This first month they come at least every week, and second month they come like once a month, less frequent. And you can have last point here, and you link all those points, and from those settlement rate you can compare with your design curve and make decision when the preload can be removed. So the best thing is, I know some builder, they know they have soft ground, they need to do preload, but they don't like to hire a geotechnical engineer. And luckily they have friends need to dump some material at his site. He said, well, why not dump to my site? I can use, my dump site is free for you to use, and he got some free material and dump over there. But that's not the right way to do, depending on how much loading you will put on it, and how long you have to dump on it. If you dump only a week or a few days and remove it, you will not achieve the intention. Even though you preload it later on, you still have problem. So those are some common misunderstanding of the preload. One is inadequate site investigation and laboratory test. Means your site investigation didn't go to, for example, too shallow. Your weak material is thick, and because the thick it is, the more settlement it will be. If your site investigation is not adequate, you will have problem later on. The other thing is because the site information you are not so clear. So when you do design, your surcharge height means your preload material is not enough, or you remove your surcharge too early. Even though some very professional guy can make this mistake. One famous settlement case is an airport in Japan. They have settlement for many years. The city's name, I cannot remember city name, but it's world famous case. The area is huge, very large, and near an island. The whole site, the whole airport is created by infill the waterfront, and the predict settlement in the airport life, they say only 1.2 meters, but actually the first 3 months they settled 1 meters, and right now they still keep on settling. So this is the common mistake we need to learn from others. The third thing is, when you dump your material on the soft ground, you need to make sure the ground will not fail. In Richmond, you can see lots of area they do preload, and they have retaining wall to keep the preload sound stable. Actually, if you look carefully at the base of the rock block, you can see they have some jaw grid, and those jaw grid actually they place over there to increase the capacity of the ground, so that you don't have stability issue. And if you do have slope stability issue, you need to put your loading on stages, stage by stage. First stage you put, for example, you need to put 3 meters. The first stage you put 1 meter and leave it on the ground and let it wait for 2 months, and then you put your second layer and fourth layer. That's the way you go. Okay. The other thing I would like to point out is, while you are doing, no matter how accurate you do your laboratory test, you do analysis, you do your design, the field observation is vitally important. You need to ask a survey guy you need to have at least 4 or 5 points and look the settlement of the ground, and to do a back calculation compare with your analysis. Okay, let's keep on going. Okay, the next one we will talk about is the pile foundation. For the pile foundation, as a build, you need to be aware that the function of pile is to pass the load from the shallow depths through the pile structure, through the pile element to the underlying hard ground. And while you put a loading on the pile, they have two resistance from the pile. One is the friction from the pile shaft. The other one is the bearing resistance from the pile tip. And for the pile shaft resistance and end bearing resistance, we have lots different way to do the calculation and analysis. Like the one shown here, this is a spreadsheet I set up by myself, and this calculation is based on the API method. API means American Petroleum Institute method. And this method is based on the field testing, and they separate it into two different pipe group, and each group they also subdivide into different method of installation. The graph I show over here, so they have different color, and you see like this one is the total capacity, this is the capacity, and this is the depth, and they have variations for sure. This because the soil layering, they varies. This is the first layer, this second layer, the third layer, and fourth layer. The pile resistance, the friction resistance is from the lateral earth pressure. The lateral pressure multiplied by the friction coefficient multiplied by the perimeter areas of the shaft is the result of shaft resistance. And the bearing resistance is the bearing area multiplied by the unit bearing capacity. So previously we say we have different type of pile. For example, we have tin pile, and when we install a tin pile, we need to install it upside down. Means the small end need to install downwards, and the big diameter on the top. That's the way, you know, we try to squeeze the pile into ground so that we have friction on the shaft. If we do otherwise, you know, it's very difficult to install. It's impossible to install, even though you install it while you put a loading on, because it tips this way. While you install a pile, the pile is not pushed against the soil, but try to leave a gap in between, so you don't have shaft resistance. Okay, so make sure you install it the right way. And the second thing you need to be aware is, while you install a tin pile, you need to be very careful to use the right size of job hammer. which means you need to select the weight of hammer and the job height, so that the potential energy is right for the pile tip. Otherwise, if the hammer is too big or you drop it too high, you can damage the timber. Right now, the people probably at my age use lots of tin pile, and they do have experience. The younger generation, because they are not using the tin pile so often, so the younger generation, they don't have too much experience. And even for the old engineers like my age, while we install the pile, I need to be full-time aside, make sure each pile is installed correctly, because we need to make sure each pile have right capacity, and we need to be sure we don't damage the piles. Sometimes the pile can be damaged at the tip, which is below the ground, you cannot see, but you still keep on driving it. You think it's driving down, but actually the tip was damaged. It's not going down. That's the thing you need to be careful. Concrete pile, they are not so often used here in Vancouver, but they are quite often used in Abbotsford, in Calgary. Pile installation, the pile type actually is very related with the location. The concrete pile install, they need equipment we call the auger. We need to auger a hole in the ground, and have a casing to go down with the auger and remove the material within the casing. This is step 1. And step 2 is you need to lower down a steel reinforcement, and then you put concrete from the tip all the way to the top. That's the concrete pile installation. For the steel pile, you can install it in 2 different ways. One way we say open end, the other way is closed end. Like closed end, just the steel pipe, actually they just a pipe, but at the end, if you have a plate to close the end, then you can install it as closed-end pile. Closed-end pile is fairly easy to do the calculation and analysis, because you have only 2 components, like we mentioned about skin friction and end. So there were lots of formula. You can lots different way to do the calculation. Easy. Different people can come up about same capacity. But if you design an open-end pile, there are lots ambiguity about skin friction, because skin friction, you have 2 components. One is skin friction from outside. The other thing is skin friction from inside. And end bearing is the annular area fairly small. So depending on which one, which condition the pile is, the open pile, they can act as a closed-end pile. In the case if internal friction is large enough, they can work as a closed-end pile. And for steel pipe pile, usually their capacity is fairly large. So when we install it, we can use diesel hammer, or we can use the hydraulic hammer. Quite often they are using for industrial facility. They are used for example, for bridges, those things. For the residential building, the steel pipe pile, we are using the screw pile. Screw pile, I can show you. This is the steel pipe pile, and here this is the open end pile. We install it with an open end. Both ends are open, and this one we enclosed with a cone shape. You seal it, then you can install it as closed end pile. Also, steel pile we can, depending on the condition, its ground is fairly gravel and very easy to be penetrated, so we can use H piles. And for H pile, when we do the calculation, depending on what soil condition it is, if you are installed in sand, the skin friction actually is from this external and internal here, the U shape, the H shape internal, and end bearing is just from the steel area. But if you are installed in clay, then the skin pipe, the skin friction is just a square. We just calculate the square area, and the end bearing is also the tip of the square. You treat it as end bearing. So there are different ways to do the calculation. Now, like I mentioned about for the screw pile look like a screw, which means while you install it, you screw it down, you rotate it, so that they don't have vibration, they don't have noisy, they don't have contamination. And you can see their diameter is fairly small. So this, compared to this here, they're quite small. So because the shaft is fairly small, you do need a plate, which is screw plate, to give you the end bearing, larger end bearing. And usually you can use a few, sometimes they have 3 screws, so that you can increase the bearing capacity. However, even though you can do this to increase bearing capacity, because the shaft is so small, so lots facility, when you do design, you do not only consider the bearing vertical capacity, but also you need to consider the wind load, which is applied horizontally. So this pile, their horizontal stiffness is small. So when you design it, you need to be careful, especially in Vancouver, Lower Mainland area, not only the wind load, but also seismic load. During earthquake, the ground shakes left and right, so you need to be careful this will not buckle. And in order to make sure the pile have adequate lateral capacity, usually we tile different pile using the structure element, so ensure the pile work as a group and have adequate lateral capacity. This is the one example that we did a few years ago in Richmond. This one is for the foundation mitigation. You see the structure on one corner left hand, they settle more than the other end. So the way right now we did is we screw down the piles just beside it and use hydraulic jack to jack the foundation up. This usually the way while you do the construction, you didn't know the ground condition quite well, and they do have soft ground, and you didn't take it into consideration. After a few years, the ground settles, the door cannot open, and the wall cracks. Usually I got a phone call every year, at least 3 or sometimes 10 times for this project. And when we come to site, we install this screw pile. This one is a case study for the screw pile for a new building. You know, when we install the building go like this way and use the slab to tie the piles together to increase the lateral capacity. and the screw pile, will go through the soft ground, and the tip will reach the hard ground, so that the plate is sitting on the hard ground, have adequate vertical capacity. This is the one, while we jack it up, we need to make lots of marks on the wall, and those ground is previously they have crack. While you jack it up, make sure the crack close, and you don't like to jack it up too much. Now we talk about 3 different ways to deal with the soft ground. Obviously, if you compare preload will, the cheapest one is excavation and backfill, and then is the preload. The preload is cheap, but we need to expose the risk of the marketing condition. The market condition can vary after a few months, so that's the risk we need to take into account. It's cheap because you just need to rent the sand, preload sand, and just a moving transportation fee you need to take into account. And second cheapest one is the replace soft ground. That the cost is acceptable, but actually they have some limitation. They cannot use it universally. The soft ground cannot be 2 meters thick. And the pile foundation actually is most expensive. But the thing is, they can install immediately. You don't need to expose yourself to the risk of market condition variations. The other thing for the preload, yes, it's cheap. The other thing is for a few months or for a year, you have purchased the land already, and some land is fairly expensive. For this 1 year, your money is actually put in the ground. You cannot use it. This is other thing you need to take into account too. If you have borrowed money from the bank, you have to pay the interest, so it can be expensive too. Okay, now we will talk about part 4. Part 4 is how to deal with sloping ground. If you recall the part 1, in BC we have 2 critical issue. One is soft ground, which I'll talk about how to deal with it. The second major thing is sloping ground. Sloping ground is the second major geotechnical hazard we need to deal with. For the ground, if they are over 10 degrees steep, then you need a significant side leveling work. For example, a low size of 10 meter to 30 meter, if you have 10 degrees, so that the difference can be like 4 or 5 meters difference. And because our house cannot, the internal grade cannot be a slope, you need to have a plate ground anyway. So you need to think of how to make use of the land. Usually you need to remove the soil on the high end and backfill the low end. But if the natural ground is over 20 degrees, then in addition to this, you may also have stability problems. Now, in order to answer the questions of how to deal with sloping ground, first of all, we need to determine whether the slope is stable or not. And second is how to, if it's not stable, how to mitigate, how to make it stable. Now, as a geotechnical, what do we mean the ground is stable or not? How we do analysis and come up a conclusion, say this is stable or not. So, first of all, we will come to site to do a field observation. For example, if we come to site, we will check if the pavement has cracked, if the tree is straight or inclined towards one direction. For example, most of the time, if the ground is not stable, most of the time the tree inclines towards the slope toe. This means over the years the ground progressively moves and the root moved from one location towards the slope of toe. That's why the tree cannot be straight. And the other thing we will pay attention is the scar or the erosion, especially if the slope is waterfront property. If the toe was eroded, usually the ground at shallow depths have some movement or even have scar on the crest on top of the slope. In large cities like in Chilliwack, in Michigan, at north side of those cities, they have lots of unstable or landslide hazard, and those municipalities they asking for permit if they have certain areas in the city development plan. If your property is within this area, they ask you to provide Appendix D, which is the permit you need to submit, signed and sealed by geotechnical engineer. They have three different permit. One is subdivision approved, which is larger area of the larger area. The second thing is the building permit, which is only for one piece of property, and the other thing is development permit, which means you have an existing house at the land already, but right now you need to do some motivation. You need to make some changes of existing buildings. Then you need development permit. And here I show you the Appendix D, how Appendix D look like. This is the name of Appendix D is the landslide assessment assurance statement. This need to be signed and sealed by the engineer, depending on what permit you are applying for. If you purchase a fairly large land and need to build a few townhouse, for example, or a few single house, then that is subdivision approved. And this probably is not very easy to read. I can make it larger for you. So basically, this is the whole thing asking the geotechnical engineer to do. I don't like to go into too much detail, but as a geotechnical engineer, we need to, each item we need to say what we have done, what we have found, are there any movement, do you think it will be an issue or not. So if you think they have no issue, then you have sign your name and then you can get permit. That means a geotechnical guy, they take a risk. You don't need to worry about it. Later on, if something happens, if they do have some landslide, the geotechnical guy, they might have some liability insurance to cover the site. Okay. But on the other side, if geotechnical guys think they do have some issues, and they have to point out what issue it is and how to deal with it. And later on, the city will also give you a permit, but the permit it comes with a condition. You need to follow those geotechnical recommendations and make sure those recommendations was fulfilled. Then you can build on this site. Now for a geotechnical guide, how we come to a site, we look around, we see all those things. That's only one side. The other side, what we will do is to make a site investigation and find out the soil condition, and then do a slope stability analysis. Usually we will build up a model. This is the one we show, the one of the model usually we are using, and right now it becomes the industry standard. What we are using is a software we call Slope W. And in the Slope W we have different layer of material. This is actually from a borehole logs. We drew a borehole and we know how the soil distribute at a site. Like this is one layer about from elevation 14 to elevation 9. This 5 meters is sandy, and this is clayey material. So different material we have. And while we're doing the analysis, we need to assign engineering parameter like shear strengths, the internal frictions of different materials. And then we will find out the factor of safety of the slope. What does it mean, the factor of safety? The factor of safety actually is the driving load, actually the resistant load divided by the driving load. The resistant load is from the soil strength. Okay, for example, we have lots of potential failure circles here. For each circles around the base, we have material, and this material they have strengths. And within this material, they also have a drive force, which is gravity load. So gravity load divided by the shear resistance. This is the factor of safety. Sorry, other way. The resistance divided by the driving load is the factor of safety. If the factor of safety is over 1.5, we say this slope is stable. For engineering slope, it's stable. But for the natural slope, if factor of safety is 1.3, still we think it's stable. For example, if this is natural ground and we found is 1.3 factor safety, in our appendix D we will say it's stable, so we don't need to do anything. But if the factor safety is less than 1.3, then we have to do some mitigations for it. This is actually one of the analysis for a particular potential failure circle. The factor safety is 1.2, so we think this is not stable. And you can also see in this potential failure slope, we divided this slope into different slides. This is one of slide. So each slide we have force, like left side we have pushing force from the upland, and we also have resistance, the same thing. So each side we have different load, and this at the base we have resistance. This is shear resistance. So we run analysis for each slice and put them together, and overall factor safety is the slope factor safety of this slope. Like this one, the factor safety is even lower. This is only 1.0. This is marginally stable. So for those things, during the field observation, for sure we can find lots of deformation of soil already. But this analysis is just to confirm our conclusion. And For example, for a slope is not stable, but we need to determine how much volume is involved. Like this one, the factor safety is about 1. That means marginally stable. The ground will fail soon. And while we are doing the development, we can still do it because we can put a loading on it. This is the loading from your structure, from your building, and here we can change the slope profile. For example, in this area, we can put some loading. We can put some like berm, a retaining wall, or an anchor, so that this slope overall will be stable. That means you need to increase your cost. So in addition to build a house, you need to make sure the ground is stable. Otherwise, if the slope fail, your structure will also fail. So that's one way to mitigate the slope, which is change the geometry if the house is located at the slope, right? But if your house is located at crescent of the slope, then you need to set back. Means you will lose some this piece of land. You will not build your foundation here. You set back to like a few meters away from the unstable area. That's the other way you can do. However, if you're setting your ground below the toe, then you have to build a slope here. Then, for example, this is potentially not stable. Then you have a slope here. You put a retaining wall here. Then you put you build your house below the toe. That's the way it goes. This is something. For example, the ground is not stable. Then you can put your anchor to make the ground stable. So for part 4, in sloping ground, my recommendation to the builder is you need to contact a professional geotechnical consultant while you are at the land building stage, so that as a builder you understand your project site at very beginning. And we will provide our geotechnical consultants for free at this stage, because we have topographic information for the for those areas potentially have hazard. For example, in city of Delft, we have the topography. If you go to the city website, you can have free topographic information for every area. It's not available for every municipal, but for those areas that potentially you have problem, usually they provide the topographic information. But even though they are not available, you can purchase it at fairly minimal cost. You can get this information. In a slope ground, for sure you need to design foundation by a geotechnical engineer, not by a structure. Structure can build the foundation fairly strong, but they cannot make sure, they have no idea whether this area will have landslide or not. That's totally different approach. The structure, after the ground fail, maybe the window still over there, even the glass is still over there, but the whole area they moved. And while you are reading, I think for the build, usually you have you have a drawing, say issue for construction drawing, you need read through it, and not only the drawing, but also you should ask him for the geotechnical report. Only with those things, then you can provide 2, 5, 10 years warranty to your project. That's the way you go. Otherwise, nobody can provide your such warranty. And in the sloping ground, all the cities, they require the schedules, the right schedules signed by the geotechnical companies. Okay, that's all I have for my slides, but we still have a little bit time, about 1 hour time. We have part 4 for removing bedrock. At that time when I prepare this lectures, I have some project in my mind, and I didn't put it into slide yet. But let's have a break, and after break we can keep on going. Okay?
Yeah.
Okay. The next we will talk about part 5, remove bedrock. As you can recall, in North Vancouver and West Vancouver, we have bedrock at fairly shallow depths. And those bedrock, they are fairly good foundation material. But because the bedrock is usually not flat, so like in North Vancouver and West Vancouver and somewhere else like in Sunshine Coast, the bedrock actually is in a mountain area, so the ground, the natural ground, is at least 10 or even 20, sometimes 45 degrees. So for this bedrock, we need to remove a portion of it to make the ground flat, or to make a few steps. In some of cities, they have limitations for how much volume is allowed to be removed. For example, in city of West Vancouver, for residential building, one single family residential building, the volume can be removed is 600 cubic meter. If your design asking for remove the volume more than that, then the city will not give you the permit. He will ask you to revise the design for the basement. Okay, if in the case we got approved and the remove volume meet city's requirement, then how we can remove the bedrock? We have 3 different ways to remove bedrock. The first of all is very conventional method, which is blasting. Blasting, you use the dynamic. You drill a borehole and put a dynamic inside, and you trick the dynamite, and then the rock will be damaged by the impact energy. Then you can remove the bedrock. That conventional way is the most dangerous way. You do need a permit, and you need the blasting company to do the work for you. Before the blasting, the company, the blasting professional guy, they will do a site survey, make sure the surrounding area is safe. If if they have any residential building, they will they have do a detailed mapping for any extinct damage. For example, crack. They will take photography. They will make sure all the utility like refrigerator, TV, everything works. So that later on, after blasting, they will come back to you, say, well, your blasting damaged my refrigerator, for example. So that's fairly time-consuming and fairly expensive. But actually, it's fairly effective way. The one time they can remove lots of material, lots volume of material. And the second alternative is the silent blasting. Silent blasting, you are using the expensive, you are using the chemical material. You also drill a borehole and you mixed two different material and mixed it with water, and then you pull the mixture into the borehole and leave on the ground for a few hours. For example, in summer it can be fast. They have 3 different types. They have like EPS 500, EPS 300, different type. They can be used at different area or different weather condition. For example, in summer you are using EPX 300, then you wait for 8 hours. After 8 hours, the ground will crack, and you don't feel any vibration, you don't feel any noisy. So it's very safe way. Usually you don't need any permit. The only noise you can be noticed by your neighbor is while you are drilling a borehole. However, this is very expensive way to do, because those boreholes, they need to be, the spacing from center to center need to be very close by, which means you need to drill lots of boreholes. And to reduce the cost, ideally you will have a good design so that the remove volume is minimized. And in this scenario, I encourage you to use the silent blast. And recently, nowadays, we have one more option, which is the option in between. You do have some blasting, and this is also managed by the hazard material, but it's not characterized as dynamite, as blast. It's not so restrictly controlled by the government. Motor company can have license to do. If you have some training, you take some training course, you can do the work by yourself. The third options, there are sometimes there's something in between. So the remove volume is medium volume, you can be used. But anyway, if you have to remove any bedrock, you need to provide the topographic for the existing condition to the geotechnical engineer and blasting company. And you also need to provide the design approved by the city so that we can determine how much volume will be removed, and give you the best design for no matter which method we are using. For the conventional method blasting, we have control blasting, we have smooth blasting, and we can generate the final products which meet your design, like the area, like the depths can be controlled. But if you would like to control in a fairly precise way, that means you need to drill more borehole. While we're doing the blasting, each hole, they have time delay so that we can minimize the vibration. and we can control the fly rocks by putting some blasting mat on top of the ground. That's the way we go. Okay, I think that's it. That's all we have.
Okay, good.